Our universe is about 15,000 million light years across. It contains 100 billion stars. It's the force of gravitational attraction that created these stars from faint wisps of hydrogen gas, and which holds their myriad forms together. Yet gravity is by far the weakest force we know. It's a paradox that this weakest of all forces could crush our universe out of existence in the black hole, astronomers' most revolutionary concept. That's the deepest mystery of science today. What happens at the center of a black hole? Red giant stars can collapse to become black holes if they're at least twice as heavy as our sun. The collapse under gravity then goes on through the white dwarf stage to the neutron star stage and beyond. As it gets smaller and gets more and more condensed, the force of gravity on its surface increases. It's harder to get away from it. Its escape velocity increases, in other words, the velocity needed to get away from it in a rocket. On the surface of the Earth, the escape velocity is about 5 miles a second. On the surface of a white dwarf, it's about 2,500 miles a second. But on the surface of a heavy, collapsing star, that escape velocity increases and increases and increases. We don't think that anything can go faster than light. Once the escape velocity on the surface of this collapsing star increases to the velocity of light, nothing can get off it, not even light itself. At that moment, we can say that a horizon, an event horizon, forms. That's a one-way membrane. Anything falling into this event horizon can never get away again. And here then we have the true collapsar, collapsed star, or equivalently the black hole, because you shine light at it, it can never get out. It is truly black. Well, this makes the black hole the most exciting object in the heavens. And we can ask, what evidence do we have for their existence?
It's been announced that astronomers at the Royal Greenwich Observatory have actually managed to weigh one of those mysterious astral phenomena.
To observe it, they actually had to use a telescope mounted on a satellite, which measures the emission of ultraviolet radiation. Galaxy NGC 4151 has as its center something very like a quasar, a mass which constantly emits pulses of radiation. A quasar is a disk of hot gas surrounding a black hole. Contrary to the science fiction stories, not everything which approaches a black hole is immediately sucked into it. 3 rings of gas actually whirl around the edge of this particular hole, and by measuring the size and different speeds at which these rings are moving, they're faster on the inside than on the outside, astronomers have measured the gravitational pull which the black hole at the center of the galaxy is exerting, and hence its weight. Now, it actually weighs the equivalent of between 50 and 100 million of our suns. It's as if around 100 million suns had compressed into this one space.
Well, it's very massive. There's a lot of material crammed in there. But the point about black holes is they're really concentrated places where matter lives. So the whole thing is no bigger than perhaps the innermost parts of our solar system, i.e. not much bigger than the sun. So there's a tremendous density of matter, and that means that the gravitational pull of this thing is very, very strong indeed.
But what new things about black holes has this discovery taught us?
For the first time, we've actually tied down a black hole at the center of a galaxy. Astronomers for long suspected that the centers of galaxies, which are collections of stars like our Milky Way, may well have black holes lurking right at their centers where the pressures are tremendously high. And in this case, it seems, from the measurements which have been made by astronomers at the Royal Greenwich Observatory using a satellite called IUE, that there is this particular black hole in a galaxy called NGC 4151, which is not visible to the naked eye, and it does have this particular mass.
Yes, it certainly is beautiful. But what interests astronomers today is how did it all come into existence? 10 years ago, we thought we had an explanation. In the beginning, the Big Bang produced a universe of hydrogen, helium, and radiation. Heat, light, microwaves, X-rays, and so on. It was all expanding, but slight variations in density, whose origin, I should stress, were completely unknown, started the gas clumping together to form the building sites for galaxies. Now, within each galaxy, the force of gravity starts pulling the gas together into gigantic bundles which can act like cosmic vacuum cleaners, sweeping up all the hydrogen in the vicinity. Here's one that becomes dense enough to detonate like a hydrogen bomb. But unlike a hydrogen bomb, it doesn't fly apart. It's held together by its own gravity. So it just sits there in space, a vast, shining, spherical hydrogen bomb we call a star. Meanwhile, the same thing's been happening to make 10,000 million other stars, and their mutual gravitational attraction holds them together in a vast celestial city of stars and gas that we call a galaxy. And galaxies themselves are gregarious. Hundreds, even thousands of them hang together in clusters. And clusters hang together in superclusters and so on. Thousands of millions of galaxies, each of them containing 1,000 million stars, one of which is our sun. And that's the entire visible universe.
Hubble's law was the first convincing support for an expanding universe and for the Big Bang.
Hubble discovered that the universe was expanding by looking at the spectra of galaxies. And that means that what he did was he spread the light from each galaxy out into its colors. And when you do that, you see that the spectra of galaxies have a certain characteristic pattern. And this pattern is due to the chemical elements which make up the galaxies. But as the galaxy is farther away, the pattern is shifted to longer wavelength or shifted to the red. This red shift tells us that galaxies that are farther away are moving away from us faster. In other words, they're moving away with velocities proportional to their distance. Now, of course, it's easy to misinterpret this and think that galaxies are just whooshing through the universe, but in fact, that's not what's happening. What's happening is that space is actually stretching. And so here's a little piece of the universe, and each of these stars represents a galaxy. And if I just stretch the rubber band, that's what happens. That's exactly the Hubble law.
The universe is expanding now, but what's it going to do in the future? Either it'll go on expanding forever, an open universe, or, if they're massive enough, the galaxies and so on will exert enough gravitational attraction to put the brakes on and start the whole thing collapsing again. A closed universe. Okay, there's a third possibility, but at first sight it seems pretty unlikely. There could be just enough mass to balance the universe precisely between these two alternatives, the so-called flat universe. The disturbing thing is that when we estimate the mass of the visible universe, it comes out surprisingly close, to within a factor of 10 of making the universe perfectly flat. But why should this be a problem? Because the universe is expanded to its present enormous size from a very, very small size indeed, smaller than an atom. To be as flat as we see it today, at half its age, the universe must have been twice as flat. At a quarter of its age, the universe must have been 4 times as flat. So near the beginning, the universe must have been perfectly flat, aimed at an ultimate state of perfect balance to an accuracy of 1 in 10, followed by 60 noughts.
Now, this may not seem terribly serious to you, but it's extremely serious to us. For you see, if I were a gambler, and I were willing to bet on what the universe should look like today, I'd find the odds against it being set up with such astonishing accuracy right at the beginning are about the same as the odds against my grandmother guessing the number of atoms in the sun and getting it exactly right. But this is so ridiculously unlikely that cosmologists have been searching for some deep reason why the universe just had to be flat because of some new physics that was built in at the beginning. And that's the way the situation was until about 1981, 9 years ago, when Alan Guth, a young particle physicist, proposed that the standard Big Bang model had missed out on one important point. What if, just after the Big Bang ignited and started to cool down, it changed phase, just as cooling water vapor changes phase and condenses into rain? But water vapor in the atmosphere often cools well below condensation temperatures, becoming supercooled before flashing into a cloudburst. Alan Guth worked out what would happen if this sort of thing took place very early on in the life of the universe.
Now, it turned out that extreme supercooling would have very dramatic consequences for the early universe. It brings the universe to a very peculiar state in which the sign of gravity is reversed. So instead of having the universal attraction of matter that we're used to, instead there's a universal repulsion, and this gives the universe the initial push of the Big Bang. And it causes a tremendously dramatic expansion. What can happen is a region which starts out more than 1 billion times smaller than the size of an atomic nucleus can undergo tremendous expansion, and in a very brief period of about 10 to the minus 30 of a second, that's a decimal point, 29 zeros and a 1, that many seconds. In that very brief period, this tiny region can inflate to something which is about the size of a grapefruit or so. And then, during the next 10 billion years, this grapefruit continues to expand and becomes the entire universe, or the part of the universe that we observe today.
And just as the surface of a balloon becomes flatter as you blow it up, so inflation theory predicts that the observable universe today should be precisely flat. Inflation theory not only rescues the Big Bang model by solving the flatness problem, but it may solve other mysteries as well, such as why the universe looks the same in all directions, and just what started matter clumping in the first place in a way which might explain how galaxies started forming.
If the universe was expanding, then it must have started somewhere at a single place and time. And the Big Bang itself should have left a further legacy, an echo of the gigantic fireball that signaled the beginning. In 1965, Arno Penzias and Robert Wilson were working on telecommunication systems at the Bell Laboratories. They were troubled by an unwelcome signal flooding their radio antenna. It was very weak, but it was also the same no matter where they looked in the sky. Unwittingly, they had found the predicted echo. Hubble had found that the universe was expanding. Penzias and Wilson had heard the echo of the fireball. One last finding would be enough to clinch the Big Bang. COBE was launched in November 1989. Its instruments are making finer and finer measurements of the microwave background. The cold dark matter model predicts that the clumping together of dark matter in the early universe should have left faint temperature fluctuations, fossilized evidence of the seeds of the early galaxies from the first moments following the Big Bang.
This is a satellite dish, the kind that's used for looking at TV satellites or for communications, like we get our data from COBE through a dish like this. And if you take a dish like this and tip it down to where it's looking at the Earth, then we see a lot of thermal radiation from the Earth because the Earth is hot. And we hook it to a speaker and you can hear the hiss, this loud hiss. Okay, if you'll now push the receiver back up, so we point up at the sky, as you point away from the Earth, the hiss decreases, but it doesn't go away altogether. And about 10% of that hiss, we believe, is the echo from the Big Bang, thermal radiation that was formed 10,000 million years ago. We are really looking for primordial fluctuations, fluctuations that were produced in the extremely early universe during the time of inflation by quantum mechanical processes. And those things have been frozen in until the time we're looking at. Because the universe is so transparent to microwaves, we can look back to a time that's only 100,000 years after the Big Bang. And as the data has been coming in, we've been processing it, checking to see it's okay, and making maps. And the first map we make, you can see, it's just uniform. I mean, you just see the sky looks the same everywhere. You don't see the galaxy or any other things that you see optically. If you take away the average brightness and expand the scale by a factor of 1,000, then you see two things, the most prominent of which is that the radiation goes smoothly from a hot in one direction to cool in the other direction. And we think that's caused by our motion. The direction we're going, we're running into more photons, and it's hotter in the direction we're leaving, they're fewer. And the other thing you can see is a band across here, which is the galaxy. But if we take away the dipole anisotropy, which we see in the next picture, the only thing you see in the picture is the galaxy. And now we can see down at a level which is more than 10,000 times the original intensity. And we see that there are no fluctuations. And that's getting to be a problem.
It's a problem because the theory can't explain how the smooth early cosmos produced the lumpy large-scale structures we see today.
If we don't find something very soon, we'll have to abandon that theory. And though I want very much to find the fluctuations, if I were a theorist, I'd be getting a new model ready.
American astronomers say they've made the discovery of the century. They've found evidence to confirm how the universe developed. Data from a NASA satellite has revealed immense faint ripples in the level of background radiation at the outer edges of space. Scientists say the ripples explain how stars and galaxies were formed after the universe began with a big bang 15 billion years ago.
NASA's COBE satellite was launched in 1989 to probe the radiation that comes from very nearly the beginning of time. For years it's been sweeping the sky. Astronomers have been looking for ripples in the background radiation. These, they believed, were the seeds out of which everything in the universe grew. Until now, these ripples have been too faint to detect. But now these ripples have been found by analysis of computer-enhanced images like this. They show the early structure of the universe when it was only 500,000 years old.
That structure has been growing under the influence of gravity to form the galaxies that we see around us. Not only galaxies, but the clusters of galaxies, the stars and the planets, and we ourselves, of course, are a part of that structure. And this new discovery has shown us that we have a clear route between the Big Bang and the present universe through a stage where the universe just showed these first signs of structure way back in those early days.
Meanwhile, back on the ground, COBE has its competitors. Scientists at the University of Manchester's Radio Astronomy Lab at Jodrell Bank are also searching for those ripples, but with a much lower public profile than NASA. The radiation from space is reflected off metal mirrors into horizontal cones. Whether on the ground or in space, the key to success in getting pictures of those ripples is temperature control. Because it is warm, the radio receiver itself emits radiation. And this noise, as it is called, can drown the signal coming from space. To reduce this noise from the equipment, they lower its temperature until it is extremely cold. Up in space, the COBE satellite is stuck with equipment which is now several years old. But the Manchester scientists and their colleagues have been able to continually update their equipment. Having installed it high up on a mountain in the Canary Isles, they expect to have pictures of part of the ripples, possibly by the end of this year. And that is important for what happened next.
It may return 4K on that.
Over in America, the COBE team had apparently beaten them to it. The satellite has been continually sending down data from space. This has been processed by the scientists, and on April the 23rd, George Smoot held his press conference.
If I can have the first view graph, well, this is a survey of the whole universe. It's just like the geological survey, a geological survey image of the whole Earth. This is us making a map of the whole universe and flattening it out, putting it on a sheet. And what we see after we remove our best model of the galaxy and so forth is that there's structure left in the map. And the structure is a very small amplitude. It shows up as temperature variations that are less than 1 part on 100,000. And that's...
But at Jodrell Bank, they thought there was something a little odd about that picture.
Clearly the pictures that appeared in the press over here in Western Europe, people interpreted as being maps of the ripples in the microwave background. And no such thing there. In fact, as I was saying, noise up from the receivers themselves.
Rod Davis maintains that the equipment on COBE was just not sensitive enough to produce a real picture. There's so much equipment noise here, it's impossible to say what we are looking at.
I was really quite annoyed when I realized later that this was not really a map of the ripples, that it is mainly a map of instrumental noise. It was a very good story, very important story, and they didn't really need to
So now the inventor of the Polaroid camera, Dr. Edwin Land,